What makes something acidic? In this video, you will find out what acids are and what the strange pH scale is all about. Acids are substances that taste sour, like the citric acid in lemons, and vinegar, which is sour wine or vin aigre in French. There are many other natural acids, such as lactic acid in sour milk and the poisonous oxalic acid in rhubarb. 250 years ago, early chemists found that non-metals burnt to form acids, so they named the gas in the air oxygen, meaning acid maker. Sulfur burns to form sulfur dioxide, which dissolves in water to form sulfurous acid. Carbon dioxide forms carbonic acid, making rain always slightly acidic. And nitrogen oxides dissolve in water to form nitric acid. However, oxygen also reacts with reactive metals to form alkalis such as sodium hydroxide and calcium oxide. So oxygen is not only an acid maker, but also an alkali maker. In water, acids give up a hydrogen ion or proton to the water molecule, forming a hydroxonium ion, H3O+. For example, hydrochloric acid produces the chloride ion and hydroxonium ion. Acetic acid, the acetate ion. Sulfuric acid, the sulfate ion. The amount of acidity can be measured on the pH scale, a measure of the concentration of hydroxonium or hydrogen ions, little p for power or strength, and capital H for the hydrogen ion. Acids can change the color of indicators. Try making your own by extracting the color from red cabbage leaves or other colored plants. Add lemon juice, then garden lime, and watch the red color gradually change through green to blue as the acid is neutralized. Perhaps the most famous indicator is litmus, which is extracted from lichens, red in acid, blue in alkali. A full range indicator contains a mixture of dyes, allowing you to measure the pH from 0, strong acid, getting less acidic, through neutral water at pH 7, getting more alkaline, to strong alkali at pH 14. The pH scale is logarithmic, meaning that for each change of 1 unit of pH, there is a 10-fold change in acidity. To understand its logarithmic nature, consider this. You have collected a bucket full of acid rain with a pH of 4, and you want to make it less acidic for watering your garden. How much neutral water must you add to make the pH change from 4 to 5? Pause the video and think. Well, the answer is that you need to add 9 buckets of neutral water just to change the pH by 1 unit, since each change in pH is a 10-fold in acidity. To summarize, most acids are naturally occurring substances which dissolve in water and are sour to the taste. Warning: only taste food substances. They are also formed when oxides of non-metallic elements, like sulfur dioxide, dissolve in water. There are several different indicators which can help us determine the acidity of a substance, and the degree of acidity is measured on the pH scale, which is logarithmic.
In this video, we are going to learn about what makes things alkaline or basic. Alkaline materials are usually used to make cleaning products, like soap, and ceramics, such as tiles. They neutralize acids and so can be used to ease indigestion and remove harmful gases from industrial chimneys that contribute to acid rain. To test for an alkali, expose it to red litmus paper. An alkali should turn the paper blue. An alkali is considered an ionic compound made using the positively charged cations of alkali or alkali earth metals from groups 1 and 2 of the periodic table. A broader definition is any base that dissolves in water, and in this case ammonia is also an alkali. All alkalis are bases, but not all bases are alkalis. A base forms a slippery aqueous solution, tastes bitter, has a pH above 7, and reacts with acids to form salts. There are many definitions for bases. In Arrhenius theory, a base dissociates in water to form hydroxide ions. The Arrhenius definition is a very narrow definition in which only hydroxides are basic. We can see that bases react with acids to produce water and salt. In Lewis theory, a base is an electron pair donor. The Lewis definition is a very broad definition in which a wide range of chemical behaviour may be described as basic behaviour. In Bronsted-Lowry theory, a base is a proton or H+ ion acceptor. Let's stick with this definition. Notice that all of these equations are equilibria. Kb is the equilibrium constant for the base reaction and describes the extent of H+ uptake by the base, B. Kb is equal to the concentration of Hb+ over the concentration of B times the concentration of H+. The higher Kb, the greater the extent of H+ uptake, so the stronger the base. Kb is associated with the pH scale. We use pH to tell us how strong acids and bases are, usually on a scale of 1 to 14, where 7 is neutral, like water. There are many kinds of indicator for pH scale. Phenolphthalein is a good indicator for alkalis. It turns from clear to pink at around pH 10, whereas methyl orange is not so good. It undergoes its colour changes below pH 7. Mostly, universal indicator is used because it has a full spectrum of colours for pH indicating. Strong alkalis include hydroxides, carbanions, amides, and hydrides of group 1 metals. Sodium hydride is known as a superbase. Strong bases are very dangerous. Why do you think this is? Strong bases are very reactive, and thus they are corrosive. Many cleaning fluids are strong bases. Organic alkalis are usually weaker. Very weak alkalis include chemicals like ammonia, which use their lone pair of electrons to accept protons. They do not dissociate in water to give a negatively charged ion, so the bond to H+ is weaker.
In this video, we're going to have a look at the pH scale and some other simple indicators of acids and alkalis. In other videos, we have seen what makes something acidic, neutral, or alkaline. We can tell if something is acidic, alkaline, or neutral by using an indicator. Indicators are substances that show different colours when they are in acidic or alkaline conditions. Litmus paper is a simple indicator that tells us whether something is acid or alkali. Litmus is red in acids and blue in alkalis. Litmus paper is made from lichens, which have been used to dye cloth for hundreds of years. It can be used as a liquid or paper. The paper is easier and more reliable. It comes as red litmus paper and blue litmus paper. Red litmus paper changes colour from red to blue under alkaline conditions, but no change under acidic conditions. Blue litmus paper changes colour from blue to red under acidic conditions, but no change under alkaline conditions. So just remember that red litmus paper changes colour for alkalis and blue litmus paper changes colour for acids. However, litmus paper only tells us whether something is acid or alkali, but it does not tell us how acidic or alkaline a substance is. For this, we have the pH scale and a universal indicator. Universal indicator is a mixture of different indicators, or dyes, which has many different colour changes, and so shows us the pH value of the solution. Again, it can be used as a liquid or a paper. The pH runs from 0 to 14, with 0 being extremely acidic, 7 being neutral, and 14 being extremely alkaline. Stomach acid is a strong acid with pH of about 2. Acid rain has a pH of about 5.5. Milk is neutral with a pH of 7. Seawater is a slightly alkaline. Soapy water is a strong alkaline. And bleach is a really strong alkaline with a pH of 13. Universal indicator is so called due to its ability to indicate the entire pH spectrum. There are other indicators that can be used that have other colour changes, but these two are the ones you need to know. We can also get even more accurate measurements of pH using a pH meter, which will give us readings to 0.01 of the pH. So from this lesson, you should now know indicators can tell us whether something is acidic or alkali and how acidic or alkali it is. Red litmus paper changes colour for alkalis, and blue litmus paper changes colour for acids. And universal indicator can give us more detail, indicating where on the 0 to 14 pH scale a solution is. Acids are from 0 to 6, neutral is 7, and alkalis are 8 to 14.
In this video, you're going to discover more about strong and weak acids and what makes them this way. The word acid comes from the Latin word acer, meaning sour, and you may have eaten some of them today. Lemons contain citric acid and makes the flavour of others seem less acidic. Tea contains tannic acid, vinegar ethanoic or acetic acid, and fizzy drinks carbonic acid. In contrast, strong acids are often used in school science labs for experimentation, but they have important uses in industry and the everyday world. Sulfuric acid, for example, is found in car batteries, but industry uses 200 million tons annually for the chemical industry. Hydrochloric acid, found in your stomach, and nitric acid are also examples of strong acids. We have established in our video what makes something acidic, that acids react with water to produce hydrogen ions, or more strictly speaking, hydroxonium ions. Strong acids, like the three mentioned above, dissociate 100% into their ions, like this. Most acids are weak and remain largely as molecules in solution, i.e. they do not ionize very much. Note the equilibrium arrow here. Acids can be identified by using full-range indicator from 0 to 7 on the pH scale. pH is a measure of the concentration of hydrogen ions. For example, at pH 0 there is 1 mole of hydrogen ions per litre. At pH 1, just 1/10 of a mole of hydrogen ions per litre. Each increase of 1 unit of pH is a 10-fold reduction in hydrogen ion concentration. So when you reach pH 7, there are only 10 to the power negative 7, or 0.0000001 mole of hydrogen ions per litre. Here there are also an equal number of hydroxyl ions, and we have arrived at pure neutral water. If you dissolve 1 mole of a strong acid like HCl in water to make 1 litre of solution, it dissociates completely into ions, so you also get 1 mole per litre of hydrogen ions and a pH of 0. To get a solution of, for example, pH 4, you need to dilute this with 10,000 times its volume of water. We still have a strong acid, but it is very dilute. However, if you dissolve 1 mole of a weak acid, like ethanoic acid, also called acetic acid, to make 1 litre of solution, it remains mostly undissociated molecules. That's why it smells. The molecules can easily move into the air. Let's say the acid is only 0.01% dissociated, so only 1 molecule in 10,000 are split into ions. Although the concentration of the acid is 1 mole per litre, the concentration of hydrogen ions is only 0.0001 moles per litre. That is 10 to the power negative 4, making the pH 4. So here is an example of a fairly concentrated acid which is weak. Here are 2 common weak acids, vinegar and carbonic acid. Vinegar is also known as acetic acid or ethanoic acid. Ethanoic acid reacts with water to produce hydroxonium ions and ethanoate ions. Strong acids, however, are totally dissociated into their ions, which is indicated by the non-reversible arrow in the example shown for hydrochloric acid and water. So a little test to summarize. Here are the 4 pictures that you saw earlier of some acids dissolved in water. Can you say which 2 show concentrated solutions and which 2 show dilute solutions? And can you say which 2 represent a strong acid and which 2 represent a weak acid? Pause and think. Well, here is the answer. A is both concentrated and fully dissociated, so strong. B is also concentrated but not fully dissociated, so weak. C is dilute but strong because it is fully dissociated, and D is dilute and weak. Most acids are commonly occurring organic acids such as you find in lemons or vinegar, which are all weak, so remain mostly as molecules and often have a smell. There are only a few strong acids, mostly non-metal oxides, dissolved in water like sulfuric and nitric acids. But there's also hydrochloric acid found in your stomach to aid digestion.
In a previous lesson, we learned about strong acids and weak acids. An acid is a substance that would dissociate in water to give a proton, or H+ ion, and a conjugate base. An acid is considered to be strong if dissociation nears 100%, and weak if dissociation is usually less than 1%. You may want to watch this video on strong and weak acids if you've forgotten the differences for acids. In this lesson, we will learn about strong alkalis and weak alkalis. An alkali is a soluble base that has a pH greater than 7, turns red litmus paper blue, and universal indicator solution green if it is weak, and blue to purple if it is strong. But in the absence of universal indicator solution, how can we tell if an alkali is strong or weak? Much like their acidic counterparts, we must consider the extent of dissociation in water. So let's have a look at sodium hydroxide as an example. In water, sodium hydroxide dissociates into an Na+ ion and an OH- ion. Since sodium hydroxide almost completely dissociates 100%, it is considered to be a strong alkali. So we use a forward arrow in the equation. So the concentration of OH- ions in a solution containing a strong alkali will be high. Other examples of strong alkalis include potassium hydroxide and calcium hydroxide. These substances, when dissolved in water, will turn universal indicator solution a very deep purple and are highly corrosive. The pH of these substances will be at the higher end of the scale. In contrast, a weak alkali is one that does not completely dissociate in water. A good example of a weak alkali is ammonium hydroxide. In water, it does not completely dissociate into its respective ions. Note the equilibrium arrow. The concentration of OH- ions in a solution containing a weak alkali will be much lower. These substances, when dissolved in water, will turn universal indicator solution a green or a light blue, and are less corrosive than strong alkalis for a given concentration. The pH of these substances will be closer to the middle of the scale. So, in conclusion, a strong alkali dissociates almost completely in water to give a high concentration of hydroxide ions, whereas dissociation for a weak alkali is much less, and therefore the concentration of hydroxide ions is much lower.
In this video, we are going to learn about acid-base titrations and how to calculate an unknown concentration for either an acid or base given the balanced equation. You can react an acid and alkali together in a controlled way by either adding the acid or the alkali to its opposite using a burette until neutralization is achieved. This is a process called titration. Once an indicator has changed colour at a specific volume of either acid or alkali, you have met the endpoint and the titration is complete. Let's consider this example of neutralization. Given the equation, you pipette 25 cubic centimetres of a sodium hydroxide solution into a conical flask and titrate it with a standard solution of 0.1 molar hydrochloric acid. Using a suitable indicator, you find that 25 cubic centimetres of the acid was required to neutralise the alkali, as found by the titration. This is the endpoint for the titration. You can now calculate the concentration of the sodium hydroxide in moles per decimeter cubed. Using the information, what do you know? Pause the video, write down the reactants in a table like this, and continue when you're ready. Record all the information you know about the acid and the alkali in the table. Your completed table should look like this. You know the concentration and the volume of the acid used to neutralize the sodium hydroxide. This is 0.1 molar hydrochloric acid and 0.025 decimeter cubed. The next step is to use the formula triangle to calculate the number of moles. Add this as a row to your table. Use the formula triangle and calculate the number of moles. Pause the video and continue when ready. The concentration is found by dividing the number of moles by the volume in decimeter cubed. Your table should now look like this. If you look at the ratio of moles of reactant in the equation, they are the same. So the number of moles of sodium hydroxide is also 0.025 moles. Again, using the formula triangle, you can now find the concentration of sodium hydroxide marked with a question mark. Try it now. Pause the video and continue when ready. The correct way to do this is to divide the number of moles by the volume in decimeter cubed. This means the unknown concentration of sodium hydroxide is also 0.1 moles per decimeter cubed. Did you get it right? Here's a challenge. 10 cubic centimeters of a sulfuric acid solution was titrated with 0.05 molar potassium hydroxide. If the acid required 20 cubic centimeters of potassium hydroxide for neutralization, what was the concentration of the acid? Follow the steps as before for this calculation. The blank table is displayed, the formula triangle is displayed, and so is the equation. Pause the video and continue when completed. Your completed table should look like this. The correct answer is that the concentration of the acid is 0.02 moles per decimeter cubed. Note there are half the number of moles of acid because the ratio in the equation is 2 to 1, where there are 2 moles of potassium hydroxide and 1 mole of sulfuric acid. Did you get it right? In summary, the steps are 1. Have a balanced chemical equation for the neutralization. 2. Set up the table as shown. 3. Use the question and write down all you know about the acid and alkali, marking a question mark in the cell to remind yourself what you are calculating. 4. Use the concentration formula to find the number of moles from a known volume and concentration. 5. Use the mole ratio to determine the number of moles of the other reagent. And 6. Calculate the concentration using the concentration formula triangle.
You likely know that sodium chloride is soluble in water. Can you think of other soluble salts? Pause, think, and continue when ready. Copper 2 sulfate is another soluble salt as it readily dissolves in water to form a solution. Grab your pencil. You can feel the pencil in your hand because a chemical message is relayed from the muscle in your hands to your brain. Potassium chloride plays an important role in nerve conduction. Without it, no chemical messages would be relayed. How would you know if a salt is soluble in water or not? Just from its formula or from its constituent ions? This is actually possible. There are certain trends observed when it comes to the solubility of certain salts. All nitrates are soluble. These are salts containing a nitrate ion, such as sodium nitrate and silver nitrate. All chlorides, bromides, and iodides are soluble, except for lead and silver. Remember that Because silver halides are insoluble, we use this to test for the presence of halides. We can distinguish between the different silver halides because they each have a characteristic color and behave differently in the presence of concentrated or dilute ammonia. All sulfates are soluble except for lead and barium and calcium. In fact, barium sulfate is so insoluble that it can be ingested and pass through our gastrointestinal tract without being absorbed by our bodies. This is because it is radio-opaque, just like your bones. This means that X-rays cannot pass through them, and because of this, an X-ray image of your gastrointestinal tract can be produced. All carbonates are insoluble except for sodium, potassium, and ammonium. Hydroxides are also insoluble except for sodium, potassium, and ammonium. We can also say that all sodium, potassium, and ammonium salts are soluble. Calcium hydroxide is mildly soluble in water. The solution is known as lime water and is used to test for carbon dioxide. If you've ever looked closely at lime water, there is a white precipitate at the bottom of the container. This is solid calcium hydroxide. Now that you are familiar with these solubility rules, try to determine which of the following salts are soluble in water: calcium carbonate, magnesium hydroxide, potassium iodide, lithium nitrate, lead bromide. Pause the lesson and continue when ready. The answer is, of the 5 listed salts, only potassium iodide and lithium nitrate are soluble in water. Although it is recommended that you learn these solubility rules, chemists have combined this data into a table called the solubility table. Why is this important, you might ask? Imagine you had to X-ray your gastrointestinal tract and were given a solution of barium chloride instead of a suspension of barium sulfate. Barium ions are inherently toxic, and this could lead to many complications and even death. Hard water is water that contains calcium and magnesium ions. This is an issue because we know that they form insoluble salts. This can be seen as limescale or calcium carbonate deposits around water faucets or at the bottom of your water kettle. These ions also make it difficult for soap to lather. Hard water is treated by exchanging the calcium and magnesium ions with sodium and potassium ions through an ion exchange resin. As all sodium and potassium salts are soluble in water, the hard water is now softened. To summarize, the solubility of a certain salt can be determined if we know the solubility rules.